Hello everyone and welcome back. In this lesson we're going to look at conservation of momentum and different types of collisions. So as a quick review from the previous lesson, we learned that Newton wrote his three laws of motion originally from a momentum perspective. And he wrote his third law as momentum is conserved. We also learned that total energy is always conserved, but kinetic energy is not always conserved. It might be, but it might not be. So when you look at different types of collisions, they are basically defined on what we know about the kinetic energy. So for example, something is termed an elastic collision if kinetic energy is conserved. And that would mean that the total kinetic energy before the collision is equal to the total kinetic energy after the collision. A collision is called an inelastic collision if kinetic energy is not conserved. And that would imply that there is a loss of kinetic energy during the collision. And then there's a special type of inelastic collision that's called a perfectly inelastic collision or a totally inelastic collision. And those kinds of collisions can be identified because the objects stick together after the collision. We're going to talk about examples of each of these in a minute. But let's first talk about elastic collisions. The honest truth is elastic collisions do not exist in real life. In a collision, there's always a loss of energy due to perhaps heat, light, and sound. So why do we talk about elastic collisions if they don't exist? The analogy is kind of like talking about friction. Frictionless surfaces. There's no such thing as a frictionless surface, but sometimes we neglect friction or pretend that the surface is frictionless so that we can just look at something theoretically. And we do the same thing for elastic collisions. So sometimes we assume a collision is elastic just so that we can talk about a theoretical model. So what does it mean if something's elastic? It means that the kinetic energy has to be conserved. So for example, in chemistry, we have a container of gas here. And inside the container, we have all these gas molecules that are bouncing off one another, and they're bouncing off the sides of the container. Well, every time they bounce or they hit each other or they hit the container, in real life, there is a loss of kinetic energy. But kinetic theory in chemistry assumes that these are elastic collisions, that there is no loss of energy, and now we have an ideal gas, one in which the molecules bounce off each other, but there's no loss of energy. In fact, we use this assumption of an elastic collision for the ideal gas loss. And so it is something that we do just to simplify something and to make a theoretical model. So in reality, in physics, most things are going to be inelastic collisions, but you might run into a physics problem that the collision turns out to be elastic. Just know it's a theoretical model. It's kind of like assuming there is no friction. So let's look at a few examples. By working through these examples, I think you'll learn the concepts a little bit easier. So our first example is a freight car with a mass of 30,000 kilograms, travels at a velocity of 2.5 meters per second. It is going to collide with a stationary car with a mass of 15,000 kilograms on a horizontal track. The cars are going to connect and roll together after impact. So again, one-dimensional collision. This is happening on a train track, and these freight cars are like train cars. So when you solve momentum problems, conservation of momentum problems. A lot of times the mistake people make is they focus on the collision, that this one train car is going to crash into the other train car. The collision is the event that we're talking about, but we don't draw a picture of the event. What we do instead is we talk about what's happening before the collision and what's happening after the collision. And so we draw a picture, we're going to apply the conservation of momentum, and then we're going to look at the kinetic energies to figure out what type of collision this is. So let's talk about before the collision. What did we see before the collision? How many objects, distinct objects, were in the story before the collision? That's what we need to draw. So let's read. A freight car with a mass of 30,000 kilograms was traveling at 2.5 meters per second. So we usually draw our objects as simple shapes, maybe like squares or rectangles or circles. So I chose a rectangle to stand for the train car. So the train car had a mass of 30,000, traveling at 2.5. It collides with a stationary car with a mass of 15,000 on a horizontal track. So before the collision, you can see that there was a car parked. This car, you can see it's moving and it's going to crash into it. So eventually it's going to crash at the collision point. And then what did it look like after the collision? The cars connect and roll together after impact. So they connect and roll together after impact. So we don't draw the crash. We draw the picture of how many pieces were in the story before the collision, and after the collision, how many pieces were in the story. There was only one piece because they connected to each other. All right, letter A. What is the velocity of the connected cars? So I wrote down final velocity equals question mark. So to solve this problem, we're going to apply the conservation of momentum. And that means that the momentum before the collision has to equal the momentum after the collision. And so I want to write that down, and I want to write the equal sign at the collision. Now, many of you will say that, why do I have to write that down? Do you know that you get a point for writing this statement down on your AP exam? So get into the habit of applying the law of conservation of momentum at the start of the story. All right, so what does that mean now? So the momentum before, it means the total momentum before. So every piece in your story gets an MV. So MV plus MV equals MV, which is why you really want to make sure that you do a good job drawing the picture. How many pieces did you have before? That gave me the MV plus the MV. And how many pieces did I have after? Only one piece, MV. But I wrote MV final here because I'm looking for the final velocity of this piece. Now I'm just going to plug in the numbers that I see in my picture. So 30,000 times 2.5 plus 15,000 times 0 equals, this piece is the both masses combined, 45,000, and then the final velocity. Now, later on you might get a little bit lazy or sloppy and might have just plugged a 0 in here right up front. That's okay, but I'm keeping my work nice and clean. And then I just do my algebra and I solve for the final velocity, and I find out that it is 1.67 meters per second. And then pause and think about it. Does that make sense? So this car was going at 2.5, but he scooped up this heavier thing now, so he's more massive, so it makes sense that his velocity would decrease. This guy was going 0, but then he got hit by the other car, so it would make sense that his velocity would increase. So yeah, that kind of makes sense. So we were able to use the conservation of momentum for problem-solving purposes to find out the final velocity of the connected cars. All right, the next question is, what type of collision is this? Well, collisions are based on whether the kinetic energy is conserved or not. If the kinetic energy is conserved, then it's an elastic collision. And if the kinetic energy is not conserved, it's inelastic. So I'm going to find out what the kinetic energy is before, and I'm going to compare it to the kinetic energy after. I'm not going to set them equal to each other because I don't know if they're equal. So I have two pieces before. So I'm going to do the kinetic energy of the first one plus the kinetic energy of the second one. So I have 1/2 mv squared, 1/2, 30,000, 2.5 squared. And since this guy has a velocity of 0, his kinetic energy is going to turn out to be 0. So I have before 93,750 joules of kinetic energy. How much do I have after? So I go over here, I only have one piece. So I'm going to have 1/2 mv squared. So I turned the 1/2 into a 0.5, 45,000. The final velocity was 1.67 squared. And I find out that the total kinetic energy after the collision is 62,750. That B there should be an A. That's kinetic energy after. So I lost kinetic energy. I had 93,000. I'm down to 62,000. So how much energy is lost? I could just subtract. So what kind of collision is it? It's not elastic. Definitely inelastic. But you remember that there's a special kind of inelastic collision when the two pieces stick together? Yep, look what happened. Two pieces stuck together. So it is a perfectly inelastic collision, or a totally inelastic collision. All right, let's look at another example. In every example, we're going to highlight a certain point. All right, in this collision, we have a grocery shopper tosses a 9-kilogram bag of dog food with a velocity of 5.5 meters per second horizontally into a stationary 18-kilogram grocery cart. The dog food bag hits the front of the cart and makes it move forward. All right, I admit this is really kind of grasping here. So you got to be shopping at Costco and you got to be buying a really big bag of dog food. But I just want to show you that there's things that would be called collisions that don't have to be two cars crashing into each other. So again, we're going to approach the problem solving by marking our collision and paying attention to what we had before and what we had after. So we have a grocery shopper tosses a 9-kilogram bag of dog food with a velocity of 5.5 horizontally, there's my x-axis, into a shopping cart. So I toss the bag, it, quote, lands in the cart. That's the collision, landing in the cart. So what do we have at the end of the story? We have dog food in a cart. So the hard part sometimes is taking the words and drawing the picture. Once you draw the picture, then it's easy to apply the conservation of momentum, because the momentum before equals the momentum after, and the momentum, the total momentum, depends on how many pieces are in your story. I have one piece, two pieces. Over here, I have one combined piece. So I have mv plus mv equals mv. This velocity final will be the final velocity that the cart inches forward. I plug in my numbers, 9 times 5.5 plus 18 times 0, so that's going to fall out, equals 27, the dog food plus the cart, and the final velocity. And the cart inches forward 1.83 meters per second. All right, what kind of collision is this? Well, I know that the dog food ended up in the cart. So the honest truth is I already know what kind of collision it is. It's a perfectly inelastic collision. But what if we wanted to know, part C, how much kinetic energy, if any, is lost in the collision? Then I'm going to have to find the kinetic energy before and the kinetic energy after and subtract them. So here again I have two pieces, 1/2 mv squared for the dog food, 1/2 mv squared for the cart. So 0.5 times 9 times 5.5 squared, 0 for the cart. I got 136 joules before, and afterward I have 45 joules. So I lost kinetic energy, which is how I know it's inelastic, and because they're stuck together, it's perfectly or totally inelastic. All right, let's look at another example. And when you have impulse, impulse is equal to momentum. An impulse is an event. An event can be a collision or it can be an explosion. So in this problem, we're going to apply conservation of momentum to an explosion. So here's an explosion example. A 20 kilogram cannonball leaves a 1200 kilogram launcher with a velocity of 600 meters per second forward. What is the recoil velocity of the launcher? So in real life, it would look something like this. We have a launcher that's got a cannonball inside of it. And then we're going to shoot out the cannonball. And the question is, what is the recoil velocity of the launcher? So recoil velocity means what is like the backwards velocity of the launcher. But maybe you didn't know that the launcher recoiled or went backwards. That's okay, because you're going to find out when we do our calculation. The calculation answer will tell you that it went backwards. All right, so I'm going to do the same thing. This time I'm going to have an explosion instead of a collision, but I'm going to look at the before and I'm going to look at the after. And I'm going to draw a picture of what I see. So here's my real life picture, but now let's draw our physics picture. So I drew the launcher, 1200 kilograms, as a rectangle, and I drew the cannonball as a circle. So that's one piece. The ball is in the launcher. It's like a combined piece. And during an explosion, a combined piece breaks into individual pieces. So after, I have the ball coming out, and then I have the launcher, the empty launcher, sitting here. So, and the question is, what is the final velocity of this launcher? So we're going to apply the conservation of momentum again. I have one piece, that's an mv, and over here I have an mv plus an mv. So every time, if you can identify how many pieces you have, you'll know how many mvs to write in your story. And I'm solving for this final velocity of the launcher, so I put the final velocity here. All right, let's put the numbers in now. So on the left, the mass would be the 1200 plus the 20. That's 1220. But it's just sitting there. The velocity is 0. And over here, I have the 1200 and the final velocity. And then I have the ball 20, and it's going 600 meters per second. So now I'm going to solve for the final velocity. So obviously this is going to turn out to be a 0. And I'm going to have to take this 20 times 600 and move it to the other side, which is going to make it negative. So when I do my calculation, I'm going to get a negative answer. The final velocity is -10. So it means that the recoil velocity is 10, and the negative tells you that it's going in the negative x direction. So even if I didn't know it was going to recoil or go backwards, that negative sign tells me the direction that it's going. So that's going to be something helpful. If you ever get a negative answer, don't panic. It just tells you the direction that the object is traveling. All right, let's go through one last example. All right, this example is a head-on collision. So we have a 16 kilogram, oops, before I start, I'm going to start this problem wrong. So don't write this down. Let me just keep on going and I'll pause and I'll tell you when you can start taking notes. All right, a 16 kilogram rowboat moving to the left at 12 meters per second makes a head-on collision with a 4 kilogram canoe moving to the right at 6. After the collision, the canoe moves to the left. What is the final velocity of the rowboat? All right, what I want you to see here is that they don't combine after the collision. So let me start to draw my picture. And again, I'm going to do this wrong, so don't write this down. All right, so I start to read. A 16 kilogram rowboat moving to the left at 12. Rowboat, 16 kilograms, moving to the left. Because it's going in the negative x direction, I wrote negative 12. Makes a head-on collision with a 4 kilogram canoe moving to the right at 6. So in terms of my words and what I drew, everything looks good. But look at your picture. If the boat's going this way and the canoe's going this way, do they ever look like they're going to collide? No. So that means that my picture's bad. So I did not draw the correct picture. So I'm going to erase this and we're going to start over. All right, now you can start taking notes with me. All right, so I'm going to draw the rowboat over here. So the rowboat is going to go to the left at 12, 16 kilograms. It's going to make a head-on collision with the canoe, 4 kilogram canoe, 6 meters per second to the right. So this looks like, because of the direction of the arrows, you can see that they're going to collide. After the collision, the canoe moves to the left at 22. Because it's going to the left, I had to put the negative sign in. What is the velocity of the rowboat? So I'm going to draw a rowboat, and I know the rowboat is 16, but I didn't put an arrow on the rowboat because I really don't know what direction it's going to go. Let's think about this for a minute. Like, could this happen in real life? So let's look over here. We got a boat. It's more massive than the canoe, and it's going faster than the canoe. So like this boat has more momentum than the canoe. So it's going to smash into the canoe. So it's conceivable that the boat smashes into the canoe and makes the canoe go backwards, and the boat also continues to go to the left. But it's also conceivable that the boat could smash into the canoe and make the canoe go to the left, and then maybe the boat kind of bounces back and goes to the right. So I don't know. So if I get a positive answer, I'll know the boat goes to the right, and if I get a negative answer, I'll know the boat goes to the left. All right, so let's apply the conservation of momentum. I have 2 objects on the left, 2 objects on the right. Neither are combined on either side. So mv plus mv equals mv plus mv final. That's the one I'm solving for. And I'm just going to plug in my numbers. But let's look closely at the numbers. So 4 kilograms times 6, that's good. The boat is 16, but I have to put the negative in for the 12 because it's going to the left. And then over here, I got the 4 and negative 22 because it's going to the left, plus 16 times the final velocity. Now I just work through all of my algebra, and I find out that the final velocity is -5. Now I know which way the boat is going. It's going that way. All right, what type of collision is this? So if the kinetic energy before equals the kinetic energy after, it would be elastic. If they don't equal, it's inelastic. So in a physics problem, it could turn out to be elastic, even though that doesn't happen in real life. So let's check. So over here, the total kinetic energy is going to be made up of the kinetic energy of the canoe plus the kinetic energy of the rowboat. Two things. So I plugged in my numbers. Notice for the rowboat, I put in the velocity of -12, but when I square it, it's going to turn positive. And I end up with 1224 joules to the left before. And then after, I have two pieces. So I did a 1/2 mv squared plus 1/2 mv squared, and I got 1168. So you can see there's a slight loss of kinetic energy, and nothing is stuck together. So this would be an inelastic collision. All right, so let's look at some summary and some key takeaways. So our discussion of linear momentum is going to be limited to one-dimensional collisions. Conservation of linear momentum always holds true. A collision is elastic if kinetic energy is conserved, inelastic if kinetic energy is not conserved, and it's called perfectly or totally inelastic if the objects stick together after the collision. When an object moves in the positive x direction, velocity is positive. When an object moves in the negative x direction, the velocity is negative. So you are now well prepared to work on your homework, conservation of energy problems.